each map instances read in the encrypted input files, okay, do the computations, and then output the tuples, the encrypted tuples. After that, the mixer randomly permute the tuples and then pass to the groupings. Okay. The shuffling phase process is carried out by the original Hadoop, okay, in the untrusted environments. Okay. So we leverage on the Hadoop efficient and well-tuned shuffling mechanisms. Okay. The verification can be done efficiently by linear scanning. Okay. And besides grouping, Hadoop also help us in handling server failures, distributed storage, and other networking issues, okay, which are all carried out in the untrusted environments. One technical detail is that because each trusted environment can only handle a small, limited memories, so it can't permute the whole things, all the tuples under one trusted instances. So we solve the issue by using a cascaded mixing to permute the tuple distributedly. Okay. So each mixer will take in a maximum number of tuples that it can handle, randomly permute them, and then pass it to its neighbors. Okay. So this mixing is very efficient. It's very efficient. Okay. It can be shown that log n divided by t rounds is sufficient to bring the distribution of the mixed sequence statistically close to the random permutations. Okay. This upper bound is shown in information hiding 2005. The upper bound is overestimated. In practice, when t is very large, for example, t can be a few thousands or 100,000s, then 3 or 4 rounds probably is sufficient. I have left out quite a number of details, for example, like key management, handling of the random nulls, and initial values. They are not straightforward. Also, in Hadoop, multiple reduce instances are carried out in a single reducer. A physical server likely to handle only one reducer. Likewise for mapper and mixer. Okay. So let us compare the simple ORAM solution with our solutions. Okay. In the ORAMs, the overhead is a log n, there's a latency due to a read and write. In our solutions, we have a smaller latency. Okay. The main reason is that in our solution, we exploit the fact that read and write can be patched into two phases, whereas ORAM cater for single read and write, and thus incur higher overhead. Okay. After all, many constructions of ORAM need to permute or obviously sort the data. So in some sense, they also need to permute the data, and in our solution, we only need to permute it once. Under our security model, we assume that the adversary can observe the following. They can observe the input size and output size of every trusted instances. They also know the source and destination of the input and output, and they also know the time and the return times of each trusted instances. And for an active adversary, the malicious adversary can arbitrarily invoke trusted instances. They can hop them. They can add and duplicate ciphertext. They also can add delays. So our security model is based on a formulation by Kennetys. Basically, we first describe the permissible data that can be reviewed during honest executions. And then we say that a protocol is modulo side private if for any adversary A executing the protocol, there's an algorithm B with access to the permissible data such that the output of A and B are computationally indistinguishable. So in other words, whatever information an adversary can obtain from the permissible, obtain from running the protocol, the adversary can also obtain from the permissible data. Okay. The permissible data that we allow for MapReduce is this: is the size and input of the input and output, and the time of revocation, and return of the trusted map and reduce functions. Okay, these are done under the honest execution. Basically, all the green yellow indicated in the figure. So the adversary is able to learn the size of the input, the number of tuples output by the map, and the number of tuples input to the reduce and the output to the reduce. If we wish to hide the output of the map, we can also do padding to hide the output size of the output of map functions. And we can show that our constructions M2R is a side modulo private. So the implementation experiments, we use Zen as a trusted hypervisor and is a VDF to load and execute trusted code. So note that the design of our solutions, it can be implemented differently depending on the underlying architectures. For example, we can implement it using the Intel SGX using similar mechanism of VC3. We also ported 7 MapReduce benchmark applications. They can be, for example, K-mean, which is compute intensive, or a word count that is network intensive. In our experiment, we use 8 compute nodes. Okay. So our trusted code base is rather small. We only need 4 trusted computation units: the map, reduce, mix, and groups. For platform related, these are the map, the mixing and the grouping. We only need to extra 300 lines of code on top of our baseline system. For the application, that means the map function and the reduce function, for all our 7 examples, the line of code is around less than 200. So total, we only need an extra 500 lines of code on top of our baseline system. For the performance, you can see that for word counts, the line of codes require the number of hypercores is very small. We only need 35 of them. These are the platform related. For application related hypercore, we cannot avoid them. These are the number of map cores and number of reduced cores. For running times, okay, let's look at the baseline. Baseline is the system that able to run map and reduce under the trusted environment. For the baselines, compared to no encryptions, that means the original Hadoop, the overhead, you can see that it's roughly 2 times or 3 times overhead. For our solutions, as compared to the baseline, is about at most around 2 times overhead. So in total, compared to the original Hadoop, our solution is about 4 to 5 times incur 4 to 5 times overheads, which is, we believe is reasonable. Okay. So in this work, we consider privacy-preserving distributed computation of MapReduce with trusted computing. Okay. For our securities, we consider execution integrities and data confidentiality. Execution integrity in the sense that we make sure that the data are correct. And we made the observations that simply running the map and reduce in trusted environment is not sufficient. The interactions leads sensitive information. And we also consider the size of a trusted code base as an important factor in for securities. So in our solution, we exploit the algorithmic structures to outperform a solution that employ generic ORMs. Okay. So our future work include looking at other distributed data flow systems. Okay. Yeah, for that, end my talks. Thank you.
Great, we have some time for questions. You mentioned for your future work looking at other data flow systems, and I guess I'm curious, you have some intuition on which ones you want to tackle next?
We are still looking into it. I'm not so sure. Yeah. Probably look at the Spark or whatever.